Welcome to your deep dive. We have a huge stack of your sources on IT certification today, and, well, we are dropping you straight into a pretty high stakes, sweat inducing world.
Oh, yeah. It is definitely not your average test environment.
Right. Because, usually when we think about taking a test, we picture sitting at a desk, bubbling in answers with the number two pencil in total, absolute silence. And I mean, sure, that's stressful, but it's a very static, predictable kind of stress.
Exactly. It's safe,
Yeah, safe. But today we are looking at the TESDA CSS NC2 Premium Assessment Reviewer for 2025 to 2026.
which is a mouthful of an acronym, I know.
It really is. For those unfamiliar, that stands for the Technical Education and Skills Development Authority, Computer Systems Servicing National Certificate Level 2. And let me tell you, this is not just a multiple choice exam.
No, not at all. It is a grueling, hands-on physical assessment.
Right, where an evaluator literally stands right over your shoulder watching your every single move.
Yeah, breathing down your neck.
Exactly. So our mission today is clear. We aren't just going to look at how to pass a test. We are going to use this reviewer to decode the hidden rules of how computers actually work, why they fail, and the systematic methodology that professionals use to fix them.
And that environment you just described, that pressure cooker, it's entirely intentional.
Really. Like they want you to freak out.
Well, not freak out, but the assessment is designed as a crucible, right? To mimic the absolute reality of working on expensive, critical IT infrastructure.
Right, because the stakes are real.
Exactly. In the real world, a simple error doesn't just mean a lower grade on a piece of paper. It means catastrophic data loss
Oh, man.
or, thousands of dollars in destroyed hardware. So the assessors, they are observing your physical habits just as closely as your actual technical knowledge.
That is wild. And you can fail instantly, right? Like right on the spot for these completely unannounced traps.
Oh, absolutely. Something as seemingly innocent as grabbing a computer component the wrong way can literally end your assessment before you even plug a machine into the wall.
Okay, well, let's unpack this, because before you can build or fix a computer, you have to prove you aren't going to accidentally murder it.
That is step one. Don't kill the patient.
Right. And the source material talks extensively about this invisible assassin called ESD, or electrostatic discharge. Now, I mean, we've all shuffled across a carpet in socks and shocked ourselves on a doorknob.
Well, no, that's that.
Yeah, that zap. But the reviewer points out that a human body can act like a giant capacitor. We can store and carry between 2,000 and 35,000 volts of static electricity without even feeling a single tingle.
Which is terrifying when you think about it.
It is. And meanwhile, the source says it only takes 10 volts to destroy a MOSFET gate.
Yeah, just 10.
10. And those are the microscopic metal oxide semiconductor field effect transistors that make up modern computer chips. I mean, it's like a static electricity supervillain trying to perform open heart surgery on a robot.
That is actually a perfectly accurate analogy. 10 volts is practically nothing. I mean, you generate more than that just taking off a wool sweater.
Wow, just a sweater.
Yeah. And those MOSFET gates inside your computer's processors and memory modules, they're incredibly thin layers of silicon. So when you introduce even a tiny, imperceptible static shock,
The electrons just blast right through it.
exactly, they have nowhere to go but straight through that microscopic gate. You are essentially punching a physical hole in the silicon.
That is crazy. But wait, if it's broken, wouldn't you just see it right away?
Well, that's the most insidious part.
Yeah.
ESD damage often isn't an immediate catastrophic failure. The component doesn't just go up in smoke on your desk.
Oh, so it just sits there silently wounded.
Right. It suffers what we call a latent defect. So it might work perfectly for a week or, a month,
Then boom.
and then it mysteriously fails under a heavy workload.
Yeah.
And it leaves you with absolutely no idea why the entire system just crashed.
See, that latent damage is so insidious. Like, you could ruin a client server and not even know about it for weeks. So how on earth do you defend against a threat you can't even feel?
What's fascinating here is how the assessors actually test your defense against this threat. They aren't just checking if you can define ESD on a whiteboard.
Right. They don't care about the textbook definition.
No, they are testing your deeply ingrained physical reflexes. Your primary defense is an anti-static wrist strap, which, you wear around your wrist and clip to an earth ground.
Okay. Simple enough.
But here is the critical engineering detail that people miss.
Yeah.
That strap contains a built-in 1 megaohm resistor.
A resistor? Why? Doesn't it just wire you directly to the ground?
No, and you definitely don't want it to. If you were wired directly to ground without any resistance and you accidentally touched a live, high-voltage power supply,
Oh, wait?
yeah, The current from the wall would use your body as the fastest path to the Earth.
Which means you become the wire, and that sounds lethal.
It could absolutely be lethal. So the 1 megaohm resistor acts as a bottleneck. It allows the harmless static electricity to slowly, safely bleed off your body while completely blocking those massive lethal electrical currents.
Wow, so you have this highly engineered tether keeping you neutralized. And the reviewer mentions a trap the assessors use to check your awareness of all this.
Oh, this is a classic assessor move.
An assessor might walk up to you, completely unannounced, right in the middle of a task, and just hand you a stick of RAM. Just random access memory, right to your face.
Yep. Just hold it out and see what you do.
And if you reach out and instinctively grab that RAM stick barehanded without first checking if you are grounded or putting on your mist strap,
That is an automatic, instant failure. You are done for the day. Pack up your tools.
just for taking something that was handed to you, that is brutal. You literally have to reprogram your basic human reflex.
You really do.
Yeah.
And if you don't have a strap handy for some reason, the reviewer outlines a grounding strap alternative.
Right, I saw that you can touch the bare metal chassis of a plugged-in but powered-off power supply, right?
Exactly. By touching that metal, you provide a safe path for that static voltage to exit your body, go right into the earth ground of the electrical outlet, and completely bypass the delicate internal motherboard components.
Okay, so let's say you've proven you won't fry the parts just by holding them. Then you face the extreme physical fragility of the hardware itself.
Oh, definitely. The physical installation is nerve-wracking.
The reviewer specifically highlights modern processors like the AMD AM5 CPUs. These things interface with the motherboard using 1,718 microscopic, incredibly fragile pins on the socket.
Over 1,700 pins.
Right.
And they're easily bent.
And the installation method is explicitly called zero insertion force. I mean, you essentially just let gravity drop the chip into place, right?
That's right, just gravity. If you press down or, misalign the tiny gold triangle marker by even a fraction of a millimeter and bend those pins.
You're out hundreds of dollars.
Oh, worse. The entire motherboard is permanently dead. It is garbage.
Oh, man. Which brings us to the next massive hurdle. So once you've safely seated that CPU using zero force, you have to manage its heat.
Yes, thermal management is huge.
Because modern processors perform billions of calculations a second, which generates an immense amount of thermal energy. And the reviewer is incredibly specific about this next step. It says you must apply a pea-sized dot of thermal paste in the center of the CPU before you mount the metal cooler on top.
A pea-sized dot. No more, no less.
And I've always wondered about the physics of this. Like, why use a messy paste at all? Why not just bolt the perfectly flat metal cooler directly onto the flat metal CPU?
Well, because on a microscopic level, those two metal surfaces aren't actually flat at all.
They aren't.
No, not even close. If you look at them under a high-powered microscope, they look like mountain ranges. They are totally covered in tiny valleys and ridges.
Oh, wow. I had no idea.
Yeah, so if you just slap the metal cooler directly onto the CPU, those microscopic valleys trap tiny pockets of air between the two surfaces. And air is a terrible conductor of heat.
Right. Air acts as an insulator.
Exactly. So the thermal paste is this highly thermally conductive compound designed to squish into those microscopic air gaps. It creates a continuous bridge for the heat to transfer from the chip to the cooler.
So without that precise pea-sized dot of paste, what happens?
A modern CPU will overheat and trigger thermal throttling within seconds of powering on, meaning it intentionally slows its own performance down to an absolute crawl to avoid literally melting.
Okay, so we've got the brain in, it's properly cooled, no air gaps. Next, we install the RAM.
Right, the memory.
And the reviewer emphasizes installing the memory sticks into very specific slots, usually designated A2 and B2, right, to enable dual-channel memory, which effectively doubles the communication bandwidth between the memory and the CPU.
It's a huge performance boost, yeah.
But then the reviewer introduces a concept called the breadboard test, and it insists that you should assemble the power supply, the motherboard, the CPU, one stick of RAM, and a display entirely outside of the computer case first.
This is a crucial step.
But I have to push back on this. Building the whole machine on top of a cardboard box outside the case, that just seems like doing the work twice. Like, why can't I just plug it all into the permanent metal case, screw it down tightly, and turn it on?
Well, this raises a really important question about efficiency versus assumptions, right?
Okay, I'm listening.
In IT, assuming your hardware is flawless out of the box is just a recipe for disaster. So imagine you skip the breadboard test, You spend 45 minutes meticulously screwing the motherboard into the metal case,
Getting it perfect.
routing all the power cables perfectly, zipping them down, making it look like a total work of art.
Right, the cable management.
Yeah. And then you finally hit the power button, and absolutely nothing happens.
Oh, no.
Or worse, you hear a continuous string of long beeps. That sound is the POST, the power on self-test.
Oh, I've heard those beeps before. It's an awful sound.
It is. The motherboard is running a diagnostic before it even attempts to start, and continuous long beeps universally signal a critical hardware failure, usually dead RAM.
Okay, so one short beep is the sweet sound of success, but long beeps mean you are in deep trouble.
Exactly. And if you build it in the case and it fails, you don't know if the part is actually dead from the factory or if you did something wrong during the physical installation.
Like, what could I have done wrong?
Well, motherboards sit on tiny metal risers inside the computer case called brass standoffs.
Oh, right, the little gold pegs.
Yeah. They keep the electrically conductive back of the motherboard from touching the metal chassis. But if you accidentally left an extra brass standoff screwed into the case from, say, an older build,
Oh, I see where this is going.
yeah, and that rogue metal peg is pressing against the back of your brand new motherboard in the wrong spot, it will cause a direct short circuit.
Yikes. So it just fries the board.
Well, usually the system's safety mechanisms we refuse to boot to protect the components from bursting into flames.
Okay, so now, because I assumed it would work, I have to take the entire beautifully cable-managed computer apart, unscrew every single thing, just to hunt down one single rogue metal screw hiding underneath the board.
Exactly. So by doing the breadboard test outside the case, on a non-conductive surface like a cardboard box, you prove that the core components, the CPU, RAM, and motherboard, actually function together.
You isolate the variables.
Precisely.
Yeah.
By building systematically, the breadboard test doesn't waste time. It saves you hours of chasing ghosts.
Okay, consider me a breadboard convert. That makes total sense. So let's say we get that single short beep. The hardware is alive.
It's breathing.
Yes, but a perfectly assembled, fully powered breadboard is essentially just a very expensive, very noisy space heater at this stage. It doesn't actually do anything yet.
Not without instructions, no.
Right, it needs instructions. We have to give it a digital soul, which brings us to the firmware and the operating system. The reviewer makes a massive distinction between legacy BIOS and modern UEFI.
Yeah, this is a huge architectural shift.
So what is the actual technical difference between these two systems?
Well, BIOS stands for Basic Input-Output System. It's the legacy firmware that has been waking up computers and handing control over to the OS since, like, the 1980s.
That is ancient in tech years.
It really is, and it was built on incredibly old architecture. It relied on a partition scheme called MBR, or the Master Boot Record.
Okay.
MBR used 32-bit values to map out the storage drive. And because of that hard mathematical limit, an MBR system literally couldn't comprehend or use a hard drive larger than 2.2 terabytes.
Wait, really? It just couldn't see anything past 2.2 terabytes?
Exactly. It was a hard limit. UEFI, on the other hand, which stands for Unified Extensible Firmware Interface, is the modern standard.
Okay, so UEFI fixes that limit.
Yes, it uses GPT, or the GOD partition table, which utilizes 64-bit values. That supports storage drives of virtually unlimited size.
Oh, that's a massive upgrade.
And furthermore, UEFI includes critical security protocols like Secure Boot, which actively checks the operating system for malware before the computer even fully turns on.
That's amazing.
Yeah, and Secure Boot is actually a strict hardware requirement if you want to install Windows 11. You can't even get Windows 11 without it.
See, the installation process for the operating system itself is also highly specific in the manual. You boot the system from a USB drive, but when you get to the hard drive setup screen, the reviewer emphasizes that you must simply select the unallocated space on the drive and just let Windows take over.
Yes. Do not mess with it.
Yeah, it says you shouldn't try to manually carve up the storage partitions yourself. Why is that?
Because modern UEFI systems require multiple invisible partitions just to function at a basic level. When Windows installs on a GPT drive, it automatically generates an EFI system partition to hold the bootloader, a Microsoft Reserve partition, and a hidden recovery partition.
So it's doing all this secret construction in the background.
Exactly. If a candidate tries to manually partition the drive like it's 2005, they will almost certainly misconfigure the UEFI bootloader.
And then what?
And the operating system simply won't start after the installation finishes. You just have to let the OS architect its own foundation.
Here's where it gets really interesting to me. Once Windows is installed and you are staring at that crisp new desktop screen, You aren't actually done.
Not even close.
You have to install drivers, the specific software files that tell Windows how to talk to the physical hardware components. And the reviewer insists there is a strict, non-negotiable hierarchy for installing drivers in the Windows Device Manager.
The order is everything here.
It says you must install the chipset driver first, then the network driver, and then the GPU or graphics driver. So let me see if I can deduce why.
Go for it.
Okay, so the chipset acts as the main communications hub on the motherboard. So if you don't install the chipset driver first, it's like trying to run before you can walk. The motherboard doesn't even know what components are attached to its own nervous system.
Exactly.
It wouldn't even know it has a graphics card plugged into it.
If we connect this to the bigger picture, your deduction beautifully illustrates why the order of operations in IT is just as critical as the actions themselves. The chipset driver literally dictates how the operating system routes data across the motherboard's physical pathways. If you skip the chipset, your USB ports might not recognize flash drives, your data transfer speeds will crawl.
And everything else just cascades into failure.
Right. Other hardware drivers will likely fail to install entirely because Windows literally cannot find the hardware.
And placing the network driver second on that list is just a brilliant defensive strategy, because if you install the big fancy GPU graphics driver first, but the file is corrupted, or I don't know, you need to download an immediate security patch, you are stuck.
You're completely stuck.
Right. If you skipped the network driver, your computer has no internet access. You can't download the network driver because you don't have a network connection to download it with.
You would be completely stranded on a digital island of your own making. You'd be forced to go find a second separate computer just to download the files onto a physical thumb drive and bring them over.
That sounds like a nightmare during a timed exam.
Oh, it's the worst.
And even with perfectly ordered drivers, a computer stranded on a digital island is practically useless today. Getting it online is mandatory. Yet, ironically, creating that physical connection to the outside world brings us to what the source material identifies as the single highest failure point in the entire practical assessment.
Yep. Network cable termination.
Making the actual Ethernet cable. I read this and thought, how hard can it be? You strip the plastic off the wire, you shove the 8 little color wires into the clear plastic RJ45 clip, and you clamp it down with a crimping tool. Why on earth are candidates failing this at such a massive rate?
Well, it is deceptive in its apparent simplicity. Terminating an unshielded twisted pair, or UTP cable, requires intense physical precision and a pretty deep understanding of electromagnetic physics, actually.
Physics for a plastic cable.
Oh yeah. Inside that Ethernet cable are 4 pairs of tiny copper wires. Every electrical current passing through a copper wire naturally generates an invisible electromagnetic field around it.
Okay, sure.
So if you place 2 straight wires right next to each other, the magnetic field from one wire will induce a stray current in the other wire.
Wait, so the wires are actually interfering with each other inside the same cable?
Exactly. That interference is called crosstalk, and it massively corrupts your data.
Oh.
To combat this, engineers twist the pairs of wires around each other at very specific, mathematically calculated intervals.
Oh, that's why they're all twisted up inside.
Yes. The twists cause the electromagnetic fields to invert and perfectly cancel each other out. It's a brilliant feat of phase cancellation.
So the physical manipulation of the wire really matters. The reviewer notes you have to strip exactly 2.5 to 3 centimeters of the outer jacket, any more than that, and you compromise the structure.
And if you untwist those wires too much before pushing them into the clear plastic connector, you ruin that noise cancellation.
So your cable might physically plug in, but it won't actually work well.
Right. It'll suffer from massive packet loss and terrible data speeds. Assessors watch your hands very closely during this task.
I bet.
Furthermore, you cannot just arrange the 8 wires randomly. You have to memorize and perfectly execute the T568B wiring standard.
Right, the color code.
You must flatten the wires and align them in exactly this order: white-orange, orange, white-green, blue, white-blue, green, white-brown, and brown.
Just memorizing that under pressure sounds awful.
It is. And then you trim them to precisely 13 to 14 millimeters, ensuring the copper of all 8 wires pushes all the way to the very edge of the gold pins inside the connector.
And then after all that, you verify the cable using a digital LAN tester. The reviewer states that if even one of those 8 pins doesn't light up sequentially on the tester, it is an immediate failure.
Yep, you have to literally cut the end off and start completely over.
So frustrating. And it also mentions you need to know the difference between a straight-through cable and a crossover cable.
Also very important.
A straight-through cable uses that T568B sequence on both ends, right, to connect different types of devices, like a PC, to a network switch. But a crossover cable uses T568B on one end and the older T568A standard on the other to connect similar devices directly, like wiring one PC directly to another PC without a router.
Exactly. And once you successfully crimp that physical cable and plug it into the machine, you have to definitively prove to the assessor that the network actually works.
Yes. And this is where the reviewer highlights a genius troubleshooting trick using the command prompt.
The ping command.
The pinging trick. This was a massive aha moment for me. You open the command prompt and you type ping 8.8.8.8. Now, that specific IP address belongs to Google's public DNS server. And DNS stands for Domain Name System, which acts like the phone book of the internet, translating readable websites into IP addresses.
Exactly. It translates names to numbers.
So if pinging 8.8.8.8 works, it means your perfectly crimped physical cable, your local router, and your ISP's connection to the wider internet are all functioning perfectly.
You have an internet connection.
But if you then type pinggoogle.com into the prompt and it fails, you've instantly isolated the problem.
It's such a clean diagnostic step.
It really is. You've proven the physical hardware is flawless, and it's merely a DNS translation issue. The computer simply can't look up the word Google in the digital phone book. I mean, assessors must absolutely love when a candidate can make that distinction.
Oh, they do. It separates the technicians who guess from the technicians who actually know. And that mindset of isolation leads us perfectly into the final and perhaps most heavily weighted section of the reviewer.
Systematic troubleshooting.
Yes. Because no matter how perfectly you crimp that cable, apply that thermal paste, or configure that operating system, the laws of entropy dictate that eventually something is going to break.
It always does.
Always. And how you diagnose a broken system is the ultimate test of an IT professional.
So what does this all mean for the candidate on the floor? Well, the reviewer outlines a strict, non-negotiable 6-step troubleshooting methodology.
You have to follow this to the letter.
First, identify the problem. Second, establish a theory of probable cause. Third, test the theory to determine the cause. Fourth, establish a plan of action. Fifth, implement the solution. And sixth, document findings.
Sounds simple, but people panic and skip steps.
And the reviewer specifically calls out the absolute worst hardware mistake you can make, which will trigger active penalties from the assessors, and that is parts swapping.
The cardinal sin of IT.
Which just means randomly replacing expensive components without diagnosing the root cause first. It totally makes me think of a terrible unlicensed doctor.
How so?
Well, imagine going to the hospital with just a generic stomach ache, right? And instead of running blood tests or taking an x-ray, the doctor just starts randomly replacing your organs.
Oh, jeez.
Like, hey, let's swap out the liver and see if that fixes it. No, okay, let's rip out the kidney and put a new one in. You would lose your medical license instantly.
That is hilarious. But yeah, it's so true. Random part swapping proves to the assessor that you completely lack a diagnostic methodology.
You're just guessing.
Exactly. If a computer powers on but has no display, a competent technician doesn't just go buy a new $500 graphics card and hope for the best.
Right.
They follow the 6-step method. They establish a theory. They test the monitor on a completely different machine to rule out the screen itself. They reseat the RAM. They listen closely for the PS beep codes we discussed earlier.
They isolate the variables.
They isolate variables until the exact point of failure is undeniably exposed.
And this rigorous, systematic approach applies equally to software threats too, like malware and ransomware. The reviewer states that the absolute first step when dealing with a malware infection is not running an antivirus scan.
Which surprises a lot of people.
Yeah, the first step is to identify and physically isolate the machine. You literally pull the network cable out of the wall.
Because modern malware, particularly worms, they're designed to aggressively replicate across active network ports in seconds.
Oh, so they just spread everywhere instantly.
Exactly. If you don't disconnect the compromised machine from the network, you might successfully clean that single computer, but it will just get reinfected immediately by another compromised machine on the very same network.
Wow, so you isolate it first?
Once it's physically isolated, you boot the computer into safe mode. That loads Windows with only the essential drivers, which prevents the malware from actively running in the background. And only then do you scan and eradicate the threat.
The reviewer takes an incredibly firm stance on ransomware, too. It highlights the golden standard of data protection, the 3-2-1 backup rule.
Every IT professional swears by this.
You need 3 copies of your data stored on 2 different types of media, with 1 copy kept completely off-site, like in the cloud. And it explicitly mandates that a technician should never, under any circumstances, pay a ransomware demand.
Never. Because paying a digital ransom actively funds criminal syndicates.
Right.
And it provides absolute zero guarantee that they will actually hand over the decryption key. They might just take your money and run.
So a robust, frequently tested 3-2-1 backup strategy is really the only true defense.
It's the only defense against data extortion. If your server is encrypted by ransomware, you don't negotiate. You simply wipe the drives clean and restore from your isolated offsite backup.
Which brings us to the final hurdle of the assessment, and apparently this is a massive pitfall for exhausted candidates.
Oh, I know what you're going to say. Documentation.
Documentation. Filling out the service report. The reviewer aggressively stresses that you must fill out the service report during the task, not at the end. Why do assessors care so deeply about paperwork?
Well, because human memory is highly fallible, especially under the adrenaline and stress of a timed exam.
That makes sense. You forget what you did 10 minutes ago.
Exactly. Assessors do not view documentation as annoying bureaucracy. They view it as the physical, undeniable proof of your methodology. It is the ledger of your logical process.
So if you fix it but don't write it down, it doesn't count.
Basically. If you successfully fix a complex network DNS issue, but submit a blank or incomplete service report because you rushed at the end, you fail the assessment.
Because without documentation, you haven't proven you are a reliable, systematic professional. You've only proven you got lucky this time.
The assessors want a technician who actively narrates their process, tests theories logically, and leaves a crystal clear, auditable record of exactly what was done, why it was done, and how it was resolved.
So let's look back at this intense journey we've been on today. We started by dodging the invisible, microscopic lightning bolts of electrostatic discharge with our 1 megaohm resistors.
You saved the motherboard.
We did. We navigated the extreme physical fragility of zero insertion force CPU pins, and we explored the microscopic thermal physics of heat transfer. We embraced the breadboard test to avoid being completely foiled by a single rogue brass standoff.
A true convert.
We brought the bare metal to life, navigating UEFI partitions and the strict logical hierarchy of the chipset driver. We stripped copper wire down to the millimeter to maintain the phase cancellation of twisted pairs. And finally, we applied the surgical precision of the 6-step troubleshooting method to diagnose the machine.
It really shows that this deep dive wasn't just about learning how to plug in a computer monitor.
Not at all.
It's a masterclass in the mindset of an IT professional. It's about learning to build with extreme physical precision, to troubleshoot with an unbreakable logical method, and to document every single step to definitively prove your competence.
And I want to leave you with a final thought to mull over. Based on a quote directly from the source material, it says, "The candidates who pass are not smarter, they are more systematic." If applying a strict 6-step troubleshooting methodology, identifying the problem, forming a theory, testing it, and documenting the results can tame the immense chaotic complexity of a modern computer system, how might applying that exact same troubleshooting approach to our own personal or professional lives change the way we solve our everyday human problems? Until next time, stay curious.